Hey guys, good morning. Hope everybody had a good long weekend, and we're going to move into chapter 7 today. And we're going to kind of accelerate our pace just slightly the rest of the way. We're going to hear today about whether we're going back to the classroom or not, but we'll find that out later. As of now, we're going to kind of get through chapter 7 in two blocks today and then on Thursday. And then early next week we'll have a lab. So we're going to try and do kind of a chapter a week. I'm going to skim over some parts and maybe take some parts out as we go along because we got 5 chapters in 5 weeks. So we're going to do as best we can to get through it, and we'll see what happens. Okay, so today we're into chapter 7. And 7.1 is what we call stoichiometric relationships in chemical reactions. So with that, hang on, I got a bug on my screen. Okay, so when we talk about a chemical reaction, we talk about the reaction of hydrogen plus oxygen to give us water. We know if we wrote that balanced chemical equation out that we would have 2 hydrogen gas molecules reacting with 1 oxygen molecule to form water. We also get lots of energy. So that 2-to-1 ratio is really important. If we break it down into something that may be simpler that kind of everybody has either seen or made or whatever, think about s'mores, right? S'mores are made of two graham crackers, and let's say for argument's sake, 4 pieces of chocolate and 1 marshmallow. So our relationship then would be 2 to 4 to 1 to produce 1 s'more. Okay, so a 2 to 4 to 1 ratio to make that 1 s'more. So depending what you had, if we just gave you a pile of reactants, graham crackers, chocolate pieces, and marshmallows, we could determine how many s'mores we could make by determining which of those, according to the ratio, runs out first. Everything else is leftover, and we call that excess. And this is really what we're going to talk about in this chapter throughout. So our reaction follows the law of conservation of mass because that 2 to 4 to 1 ratio, 2 of one, 4 of the other, 1 of the third, produces 1 s'more. So this what we start out with the mass of the reactants ends up with the mass of the products as well. So that works. The problem is the relative amount so the number of moles of one to another is what we're looking at as well when we relate it back to chemistry, and that's going to be what we call our mole ratio. We're going to work with mole ratios a lot moving forward. We've already seen it some in chapter 6. We're going to keep looking at it as we continue along. So we were supposed to do mini investigation 318, but we can't do that. So I'm going to look at, just real quick, an example here on this particular subject. So an example here. So if we take, in this case, it says ammonia decomposes, and if you've got 5.2 moles of ammonia, how many moles of hydrogen could you produce? So the first thing we have to do is be able to get a balanced chemical equation. So ammonia is NH3. We can see that the only thing it's going to break down into is its individual constituents, which is nitrogen and hydrogen. We know that nitrogen, hydrogen, way back is diatomic, so H2 and N2. And then we balance the chemical equation with 2 coefficients, 2 here and a 3 here. So now I've got a balanced chemical equation. That's mandatory. You got to have the balanced chemical equation to be able to do any of these questions correctly. So once I have that, normally we would find the number of moles of ammonia, but they gave it to us. Okay, if they gave us a mass, we could also find it just by dividing by the molar mass, but we don't need to. They gave it to us here. So the next thing we go to is our ratio of ammonia to hydrogen. That ratio is 2 to 3. So if we have 5.2 moles, how do we get to this 7.8? Well, it's right over here. We've seen this in the book. We take 5.2 moles of ammonia, which we have, and our ratio is 3 moles of hydrogen to 2 moles of ammonia. Now, the reason we set it up as 3 over 2 in this scenario is because when we do this multiplication, we want the units moles of ammonia to cancel out and leave us with just moles of hydrogen. So what we would do in that situation is take 5.2 times 3, take that number, and divide it by 2. Going to give us 7.8. Okay, so that's how we get to that particular answer. pretty simple calculation. It's the initial part of what we're going to see moving forward. So I'm just going to kind of, that's really it for the beginning for section 5 or 7.1. So I gave you a couple of questions that you can work on in that one as well. Just to practice using mole ratios. So getting used to setting them up like this again. So setting them up and working with this part of the calculation right here is really important. Being able to go locker. I mean, it's easy if it's a 2 to 1, you just multiply by 2 or divide by 2, depending which one we have. But these are a little more complicated. We've got a 2 to 3 or say a 5 to 4. Setting these up and finding out the other number of moles that we need. That's really important because it's going to be one of the in-between steps as we move forward. Okay, so I'm going to leave you with that one right there, and I'm going to do 7.2 as well right away and assign both at the same time. So I'll get to that one right now.